Hello, this is Gurumurthy Ramachandran. In this lecture, we are going to continue with our discussion on Bayesian decision analysis. And in the first section, we are going to talk about the parameter space and what we mean by that. The original Bayes theorem, as we discussed in the previous lecture, can be directly applicable to discrete choices. And we ended the previous lecture with choosing between exposure profile A versus B. But in reality, we are not interested in distinguishing between just two exposure profiles. Instead, we are interested in distinguishing between five populations of exposure profiles corresponding to the exposure zones 0, 1, 2, 3, and 4. And just to review again, the key concept in our discussion so far has been on decision distributions. So we start off with a prior decision distribution, which represents our professional judgment regarding the probability of each of the exposure ratings. Then we have a likelihood decision distribution, which is the set of probabilities of each exposure rating calculated using only the collected data. And then the posterior decision distribution, which is the set of probabilities of each exposure rating calculated using the Bayes equation. But now we have to modify the Bayes equation so that we are looking at populations of exposure distributions and not just two or some discrete number of exposure distributions. So you see this rather complicated formula now. You can still see the structure of the Bayes equation. So we have the prior, which is the probability of a particular population of exposure distributions being correct. Then we have the likelihood, which is the probability of observing the data given each combination of geometric mean G and geometric standard deviation D, and the families of G's and D's corresponding to each population. But now we have to integrate the entire Bayes equation over all combinations of geometric mean and geometric standard deviations corresponding to each population. And what we will obtain is the posterior distribution, which is the probability of a given population of exposure profiles being correct given a set of monitoring data. So the Bayesian decision analysis is going to help us distinguish between five populations of exposure profiles, and these correspond to our exposure ratings. So the way to interpret these populations is that all combinations of geometric means and geometric standard deviations that lead to a 95th percentile that is less than 1% of the OEL would be an exposure rating 0. And all combinations of geometric means and geometric standard deviations that lead to a 95th percentile between 1 and 10% of the OEL would lead to an exposure rating 1, and so on. So we can look at the parameter space as shown in this diagram. So on the x-axis, we have the geometric mean on a logarithmic scale, and on the y-axis, we have the geometric standard deviation. And we start off the parameter space at a geometric standard deviation of 1.01. So it's not exactly at 1, because that would imply that all the exposures are identical. And we constrain as a default the geometric standard deviation, the upper limit, to be 4, although we can extend it beyond 4 if we need to, and we'll discuss that later. And we have these slices of the chart shown here marked as 0, 1, 2, 3, and 4. And the way to interpret this is that in the exposure zone, let's say that is marked 1, any combination of GM and GST in this region would lead to a 95th percentile that is between 1 and 10% of the occupational exposure limit. Similarly, in exposure zone 4, all combinations of GM and GST would lead to a 95th percentile that is greater than the OEL. So that is the way to interpret this chart, and this is called the parameter space. So what does it mean? So let's say that we have some data points and it leads to a likelihood function with a certain probability in categories 3 and 4, and also in category 2, actually. And in this graph, we are observing the parameter space GM versus GST from the top. And you can see that the likelihood function is elevated a little bit in category 2, a lot of it in category 3, and a little bit in category 4 as well. So if we were to consider this as essentially like a cake, and we were to slice it along these diagonal markings shown corresponding to the boundaries of the parameter space, then the volume of the cake in each of these regions would correspond to the probability in that exposure rating. And we can see that for this particular likelihood function, the volume of the cake has a value that's very low in category 0 and 1, slightly higher probability in category 2, a lot of it in category 3, and quite a bit in category 4 as well. So the volume of the cake in each one of these corresponds to the probability in each exposure rating. We can look at the profile from different perspectives, and you can see that this is the likelihood function in parameter space. And we can see that on the x and y axis, we have the geometric mean and geometric standard deviation. And along the vertical axis, we have the probability and the probability density, and the volume underneath this cake or mountain or whatever you want to call it is the probability in each of these exposure categories. And these would then be placed into each one of the 5 exposure ratings. Coming back to our standard way of looking at the probabilities, here I'm showing the prior distribution with a probability that is highest in category 2 of 0.5 and smaller probabilities in the other categories. And we can have a prior be non-informative or informative. For example, a non-informative prior is shown in the figure on the left-hand side, where the probabilities in each of the categories is 0.2. We are essentially saying that we don't know if one category is more likely than the other. So we are, in the form of the prior, providing no information at all to our decision making. The figure on the right-hand side is considered an informative prior because it is showing that category 2 is more likely than the other categories. So there is some information being provided here. Then we come to the likelihood decision distribution, and this is the same familiar example from before. So we have 3 data points, and we can obtain the probability density function corresponding to these 3 data points as shown in the previous figures where we looked at that 3-dimensional cake, and we can find the volume of the cake in each of the 5 exposure ratings, and we find out that the volume in category 2 is the most, and so that is about 66%. So that is the probability that these 3 data points come from an exposure profile that is most likely to come from the population of exposure profiles corresponding to category 2. We can then combine the prior with our likelihood to obtain the posterior decision distribution. If we were to use a non-informative prior, meaning the one that is the same probability across all 5 categories, then the posterior decision is exactly the same as the likelihood. And this is intuitively obvious because we are saying that our prior is providing no information and only the data are. So the likelihood decision becomes the posterior decision. However, if we were to use an informative prior, which says that category 2 is more likely than the others, and we combine that with our likelihood chart, which shows also that category 2 is more likely, then the posterior is also going to be category 2, but with a much higher probability in category 2. Here I'm showing essentially the same thing that we discussed. If we have a non-informative prior that is shown on the top right-hand side chart, and we combine that with our likelihood, the posterior is identical to the likelihood. However, if we have an informative prior, we combine it with the same likelihood as before, corresponding to the 3 data points, we have a more confident posterior, meaning that there is more probability in category 2, almost 86.5%. So the point shown in this chart is that the likelihood function is the same for both sets of decisions, but since our priors are different, in one case we have a non-informative prior, in the other case we have an informative prior, this leads to different posterior decision probabilities. So the previous slide showed the standard way of looking at the probabilities, but what I want to show in this graph is the behind the scenes calculation of the Bayesian integrals of the probabilities corresponding to the prior, likelihood, and posterior. So again, using the analogy of a cake, so if we have a non-informative prior, in the top left-hand side, I'm showing the flat prior, which means that for all combinations of geometric mean and GST, we have a flat layer centered at 0.2 probability. Whereas if we have an informative prior, that figure is shown on the top right-hand side, and you can see the probabilities corresponding to each one of the 5 exposure categories. And by necessity, since we have arbitrarily specified our informative prior probabilities, they look like human-made construction. But the likelihood function in the middle part of the slide is from 3 data points and assessing the populations of exposure distributions from which these 3 data points could have arisen. And each one of these exposure profiles is considered to be a log normal distribution. So the middle part of the graph shows the likelihood distribution. And what it is showing is all possible combinations of geometric mean and GST that lead to exposure profiles from which these 3 data points could have come from. So if we have a GM of 0.1 and a GST of 2.5, that corresponds to, we are very close to the peak of this mountain. And we imply by that that is an exposure profile that is very likely to produce those 3 data points. Whereas a GM of 0.1 and a GST of 3.5 also has some probability, but a much lower probability of producing these 3 data points. And likewise, a GM of 0.1 and a GST of 2 has a very, very low probability of producing these 3 data points. So in the bottom part, we are showing the posteriors corresponding to the non-informative and the informative prior and the likelihood. And we see that the 2 posterior distributions look somewhat different, although they are still centered around the exposure category 2.